Let us first start with a simplification of the viral inactivation operations. Viral inactivation consists of three main parts. 1. Lower the pH to a desired set point where, ideally, any viral particles are susceptible to irreversible acidic denaturation, but one where the damage to the drug substance may be kept at a minimum. 2. A time-based hold to ensure the low pH conditions have been reached or completed for the inactivation of the virus and the viral burden. 3. Finally, a reversed titration back to a physiological or other buffered pH condition which is favorable to both drug substance stability and further processing. A number of challenges surround this perceptively simple operation. Even in a manual viral inactivation process, there are approximate zones for optimal operation, but there are challenges to optimal operation and process development. For example, titrating too slow is both inefficient for cycle time and prolong low pH stress conditions, while titrating too fast can create localized, hyperconcentrated regions of damaging pH conditions. Additionally, short hold times could provide insufficient time for complete viral inactivation. However, prolonged low pH exposure could potentially damage or inactivate product, especially proteins and other enzymes. This may cause conditions such as deamidation, denaturation, aggregation, or other quality attribute changes. See now the zones of operation or tolerance zones indicated by green bubble. In a typical manual process, an aliquot of acid titrant is added and allowed to mix for a period of seconds. For traceable recording, the pH is checked by a standalone meter, of which the measured value is generally recorded manually. Even if automatic, the value is recorded as a single time point and later correlated to a titrated volume. The process is then repeated en route to a target pH, commonly around pH 3.5. Once at the target, the pH is held for a time-based inactivation of viral particles and then eventually reverse titrated back to a physiological or operational pH. Along the way, pH overshoot is to be avoided at all times. However, if overshoot occurs, some processes allow pH correction with a reciprocal base to return within operational tolerances. In reality, even our manual titrations follow kinetics similar to the dashed line profiles. These kinetic profiles, in addition to the data from intermittent sampling, is full of lost process insight and otherwise vital to truly understand a process. But it is also easy to overlook, especially with many legacy methods. When we have access to kinetics and ease of data overlay, we can begin to ask questions about what causes anomalies and understand the operation actions or process parameters which may come to influence them.